I lost my paper. We are discussing the LCA Problem Revisited, which is, it's a fairly simple problem. It's an elegant problem, and the solution is, again, elegant. And it's easy to define, and it has wide implications. It has a lot of practical uses, from compilers to networks to a whole bunch of other places, and databases, indexes, and everywhere. So it's sort of neat to see a solution to the problem, which is both easy to understand and simple to actually implement. So if you search on GitHub, there are like at least 10 or 15 very readable implementations in almost every language that I could think of implementing it in. No Erlang, unfortunately. Huh? Yes. No. Okay. So let's see the problem statement first. Given a tree, so you can see a tree over there, we want to find the least common ancestor of U and V, which basically means that you want to find the shallowest, the lowest node that is a common ancestor to those two nodes. So the furthest from the root and is an ancestor for both these nodes. So, LCA of T, T being the graph here. So I'm sort of following the terminology which has been used in the paper, so that it's, if you're following along, it's you can sort of match things together. So yes. So it's the problem was, it's a fairly old problem. So it was first put forward in 1973 by Aho, Ullman, and Hopcroft, and a lot of people over the years have suggested solutions. So Harrell, they suggested in 1984 O of n log n, O of n and O of 1 lookup solution. And I guess it's pertinent that I specify that what we are looking is what the full problem statement is to, in some way, pre-process the tree such that you can answer any LCA query. So you take the tree, you do some munging on it, some data processing on it, and then you get some data structure that you can query for any I and j, any U and V in that tree. Because you could do, if you were going to do it just once, then you would do a DFS and then you'd be fine. So I guess I do want to draw something, just a little thing. Do we have a whiteboard marker, please? It's not important, but can anyone see this? Or is it too out of place? Okay. Doesn't matter. I will get to it on a slide, and I'll have to re-explain it, but it's fine. Just to get some things out of the way, everyone understands big O notation, right? Everyone understands dynamic programming, what it entails, how, when, and how it's applicable. Yes, 2 slides. So Okay, so we have the LCA problem, so that's that. Let's talk about a different problem first. So range minimum query. So the range minimum query problem is, and I'll get to why I'm talking about the range minimum query, is um, given an array like so, if I ask RMQ of I and j, then you pick two indices, two elements, and I want to find the minimum element between those two indices. So in this case, 3 and 7, RMQ of 3 and 7 is the element at the fourth position, which is 7. Am I looking over there? So that's the definition of RMQ. The reason why I mentioned that is because the LCA problem can be reduced to RMQ problem, and hence, if we know the answer to an RMQ problem, we can sort of get the answers to the LCA problem. So first, let's get the notation out of the way. So whenever I talk, about any of the algorithms in this paper, and we talk in two terms, and the notation is Fn and Gn, wherein Fn is the big O time complexity of pre-processing the data structure, pre-processing the input, and Gn is the complexity of actually querying this data structure to answer the question which you asked. So you want both of those to be fast. You don't want it to take too much time just to build up your index or build up your initial data structure, and then the rest is fast or something. So you want to sort of get the best of both things. So some previous work, I sort of covered this. The first after 1973, when the problem was first proposed, they did give a solution to that problem, which was O of n log n, comma O of 1 solution, and I'll cover what that solution was. And then, over time, better solutions were proposed, which have got us to the stage wherein we can say we are at O of n processing time and O of 1 query time solutions. So, so how do we? First question is, how do we reduce the LCA problem to an RMQ problem, right? So first thing that we sort of need to understand before we get to that is an Euler tour. An Euler tour is that. So let's say you have this tree. The Euler tour is basically a depth first search, and every time you visit a node, you write it down. So in this case, you start at the root node, so you write down 3. You go and go down, you write down 2, and then you come back up and you write 3 again. And then you go to the second child node and you write its DFS in the same way. So you get this whole traversal, which is Euler tour of the tree that you have. It all came up at once, but it was going to be a question: how big do you think the Euler tour is? It is 2n minus 1 nodes long. So once you have this, you can, so once you have the Euler tour, in addition to that, you also sort of can keep track of the levels of the node. So by level of the node, I mean how far are they away, how far away from the root node are they. So like in this case, 3 is 0 distance from the root node, 2 is 1 from the root node, and so on. So you have another array which just gives you the levels of all the nodes in the tree. So in the paper, and so you know how to construct a Euler tour. So you can say that, in the same notation that I described earlier, you can say that the solution for the RMQ from the original tree that we got is some function of 2n minus 1, so the number of nodes in the array, plus O of n, because you can do a depth-first search traversal in O of n time. And the lookup is some g of n minus 1, g of n minus 1 function, and we'll get to that again, and plus O of 1, which is the cost of turning it back into the solution for the LCA problem. The reason why that's O of 1 is because with the LCA, you sort of know which index. If you do the RMQ on the LCA, you know which index it would be, because the data structure that we got over here sort of tells you which index node, the contents are the index. So it sort of tells you which index, which node in the tree is the common ancestor, essentially being the shallowest node. So a question here comes around as to why does this actually give you the correct answer? Like if I ask the LCA of 1 to 5, we know that the minimum of 1 to 5, the range minimum query gives you that the answer is 3. Why is that? Why is that the correct answer to the LCA problem? So if you sort of look at the way the Euler tour is constructed, you would see that you would visit the root, the parent node, and then you would visit the children node, and then you would go visit the parent node, the upper node again, the ancestor node again, and then you would visit another node. So if you had, so if you were finding the shallowest node for 2 parts of this tree, and you had the tour which went from here all the way and up and down again and reached this node, you must have visited the ancestor nodes at least once. You may have visited it multiple times. So like in the case of, so if I was to ask you the LCA for 4 and 6, you would visit 3 multiple times. Like you would, well,
2 and 6.
Yes, 2 and 6. You would visit 1 multiple times, but you would visit it at least once because of the way you construct the. Because if you weren't, then it would break the definition of DFS and yada yada. So this is sort of a complete example of how this goes around. So I have a tree, everything is labeled. So the first step, E represents the Euler tour of length 2n minus 1. So you go down and you start constructing. So it gives you 1, 6, 3, and so on. And then you have the levels array, which gives you the level of each of these nodes as you visited them. And then finally, you have this representative array. So the representative array is is fairly simple. It just gives you the first occurrence when the node at that index occurred. So if I was to look at, let's pick a nice one. So let's say R of 2, right? The first time 2 occurred in the Euler tour was at the 8th position. So that's what it gives you. So if I was to say I want the LCA of some x and y, then it would be the RMQ of the levels of x and y, and you take that result, and then you figure out the corresponding entry in the Euler tour, which would give you the position of the minimum of the two nodes that you wanted, and hence you would, from the Euler tour, you would get the position of the node which was at that point in the Euler tour. So in this case, let's say, yeah, so that's the expression. So LCA of x and y, so in this case, I'm taking 10 and 7. So we go to the representative array, and we figure out the first occurrences of 10 and 7, and it says it's at position 14 and 11, and then the expression above says, okay, I'll find the range minimum query in the levels array for the positions 11 to 14, which turns out to be the position at the position 12, and what you get is actually 1, and you look up the position, the corresponding position in the Euler tour, which gives you the position in the tree. So you get 9 from the RMQL, and then from 9 you look up and gives you the I lost myself. Yeah, so you look up in the Euler tour and it gives you 9, and that is the LCA of 10 and 7. Is that clear, or did I confuse everyone? Okay. So 3 years. So okay. So what is the complexity of getting all this stuff? To get all this stuff. So as we said earlier, we talk in pre-processing and query time. So first, pre-processing, right? So you're constructing these 3 arrays, which can be constructed straightforward in O of n time, basically while doing the DFS, while you are generating the Euler tour. And then pre-processing the L, and pre-processing L to get RMQ, again, 2n minus 1 because of the sheer number of nodes that you have now. And then the query complexity is whatever is the complexity of querying doing the RMQ on L, followed by the array references that we had to go through. So let's say they are all constant time, so O of 1. So what we finally get to is this expression, and this sort of forms like a basis of our further discussion. So the rest of the stuff is leaving LCA and saying that whatever be the solution, so whatever is the solution of RMQ, we can plug that solution into this expression again, and we'll get the complexity of the LCA problem. So let's just worry about RMQ solutions from now on. So the paper exposes us to 3 solutions. One is, and we'll go over them one by one. So the first one is, pretty simple. You get your array and you do RMQ on every single pair. Brute force. Just get it done. Make a table out of it, and whenever you want the answer, you basically go to the table, say I want I and j, I is this, j is this, array lookup, and you have the answer. It's a naive solution, so it's the first one, and you get O of n cube as the answer, as the complexity for the first one, for the preprocessing, and O of 1 for the lookup. And if you know dynamic programming, you can do a little better. Basically, instead of keep on recalculating stuff, you could calculate one thing and use that to calculate a slightly bigger answer. So if I was, okay, short example. Yeah, this is not going to work. Anyway, so keeping dynamic programming in mind. So if given an array, you can basically take, you take the, what you want to get is this sort of kind of works. So what you want to store in dynamic programming, you basically want to formulate a table which gives you answers to solutions which are derived out of previous answers, hence reducing the amount of lookup that you need to do. So amount of computation that you need to do by building on previous answers. So what you have there is a table which is indexed with I and j, wherein I is the starting point in your array, and j is the length of the array of the run to j to the endpoint. So in that case, m of 3, 0 is the sub array which starts from position 3 and ends at position 3. It's a length 0 run, and 3, 1 is length 1 run, and 3, 2 is length 2 run. And the solution on the slide over here sort of builds on that in the sense that in the naive dynamic programming solution, you would have n squared, you would do n squared computations because you would have n rows and n columns, one for every combination of starting at the 0th position, going up to the nth length, and then starting at the first position, go to n length, second, third, so on. So we can do slightly better. Instead of generating it for all possible combinations, what we can do is generate it for powers of 2. So why is that better? So if we are generating it for powers of 2, the number of rows in our dynamic programming solution answer, in the dynamic programming solution, reduces from n to n and log n. And now you have a pre-processing time of n log n, because what you're keeping track of here is runs. The first row is run of length 0, so it's same as previous. The second row over here is basically run of length 2 to the power 1, and then 2 to the power 2, 2 to the power 3. So it gets bigger exponential in powers of 2. And the way you, so if you were looking at the recurrence relation to sort of build this table, this is how it would be. So you have, so to construct m of ij, you can look at the row above it and then select the answer which was right above it, basic dynamic programming thing, which says the answer is either the one which is just smaller than this, or it's the answer to the one which is, I guess, to the right of the solution. So the second part. So it says the same row, and then progress it by. Can you see my pointer? Yes. So it's either in here, which is the row above it, or it's in the one next to it, which is 2, and because it's of size 2 to the power, it increases in powers of 2 to the in powers of 2, so it's I plus 2 to the power j, and the row above it. So that sort of gives you an idea about why this works. And as I said, this can be built in n log n time because the amount of data that you had to pre-compute is lesser. And then you have bigger chunks that you use. It'll get clearer in this slide, I promise. So this is all fine. And what we have till now, you could answer the range minimum query instantly if the I and j that you were asked for was the exact size of the ranges that you were calculating. If they were powers of 2, you could get the answer instantly. You would do a O of 1 lookup, and that'll be it. But it rarely happens that you would get like an exact power of 2. So instead, what you can do is find 2 ranges which overlap, and then you know the minimum of those 2 ranges. And if if the I and j are composed of 2 overlapping ranges, and you find the minimum of these ranges, then you found the minimum of the full range. So you have some range which is 2 to the power k elements long, and another overlapping range which is 2 to the power 2 to the k elements long. You know the minimum because you calculated it in the pre-processing step, and then you can do a single you can do a minima operation on the answer of those, and you get the answer to the full range that you have here. So that's what the what this also gives you is, RMQ of ij is a direct lookup if it is if it satisfies this this expression, and the idea here is to find the largest overlapping segments which you have pre-computed, and you find minima, and you are done. Yeah. So as I said, the complexity of this is O of n log n because you had less data to compute, because your number of columns were in the powers of 2, and the lookup complexity doesn't change because you're doing constant time operations. You are either looking up from the table that you calculated earlier, or you're looking up the value from the table and doing some minimums on overlapping ranges. Again, they're not dependent on the amount of input that you have. So that's sort of the second solution. Now, I'll take a slight segue from, slight deviation from the paper's order, and then come back to it, is this definition of the +1 -1 observation which the paper talks about. So going back to our tree structure, which gave us the array structure for the array for doing the RMQ. If you see the levels they always vary by +1 or -1 from the previous value. And if you think about it, the reasoning for that is either you're going from the parent to the child or the child to the parent. So it's always +1, -1, +1, -1, +1, -1, +1, -1. So given that, just keep that observation in mind for the next part, and this observation will give us a O of n solution. So let's say you have the array, the Euler to array that you got, and you divide it into blocks of size log n by 2. So what you get is the number of blocks would be 2n by log n. So you have that many blocks, and now you can do the same kind of thing. And if you consider this and compute the complex, and you feed it back into the n log n solution problem, what you end up with is sort of solving O of n, where now n is the original number of values and not n log n. You're solving basically smaller problems where on the bigger solution to get the bigger solution. So let me progress one more. Much clearer with the drawing, but okay. So consider each one of those blocks, and we call each one of them as A prime. So every element is every element in A prime is the minimum of that block of A. So you do the range minimum query on that block, and you find the minimum, and you store it off over there, and then you have these. You know the minimum of each of these blocks, and then you construct another array, which is B, wherein each of the values gives you the place where the minimum that you computed for A prime, each of the log n n by log n by 2 size blocks, and that sort of gives you a reference up. So taking a concrete example sort of will help. So let's say you have this array of length 16, and my original assertion was, let's divide it into many blocks, each of size log n by 2. So each block is of size 2. So there are a total of 8 blocks. And in each block, we do the range minimum query. So we find the minimum element of each of these blocks, and we store it away in A prime. And in B, we store the location of the value in A prime. So it sort of has an index into where the minimum came out of. So, 10th is at the 0th position. So if I was to ask you, what is the minimum from 0 to 1, the range minimum query of from 0 to 1, then you would just go to the 0th position in B, and you would know the answer to you would know the answer instantly. It's at the 0th position in the original array. And same way, if I was to ask you what is the answer for 2 to 3, I would instantly know, go to the 3rd position, and that's your answer. So now that you have this, you can sort of figure out how to combine these and get an answer. So let's say if my query was to find me the minimum element from 0 to, let's say, 0 to 4. Then I would be 0 to 3. Let's full ranges. So I would consider the minimum value of the first two blocks, which I know I have the answer for that ready. So it is, it's the minimum of A0 and A1, because those are the minimum of those locations, which turns out to be A of 1. And then I can go to B of 1 and find out where that answer lies in the original array. So 7 is actually in the third position, so I can reply with the answer. The minimum of A of 0 to A of 3 is at position 3 at the query time. But again, this is completely dependent on the fact that your question is exactly aligned to the beginning and the end of one or more of these blocks. So we'll sort of massage it into a better place. Okay, so before doing that, I sort of glossed over it earlier, but the complexity here is, so you have O of n log n from the dynamic programming solution for pre-processing, but we divided each of our data set into things of sizes 2n by log n. And so we take that and we plug it in place of the n. And now we have, by powers of math, O of n log n pre-processing and O of 1 query time solution. You just plug that value in the n log n and you sort of get it. And again, it's O of n, so it doesn't have to be exact exponents matching, but that's what that sort of is the power of O of n. So you get that. So now we come to the question of how do I answer a generic RMQ of I to j, wherein I and j can be anywhere in my array. It's not required that it's aligned to some particular block. So the first, the way you answer this is you find the minimum from I to the end of the block that it lies in, and then you find the minimum of all the blocks in the middle, all the complete blocks in the middle, so which goes from, so first you find from the RMQ from 1 to end, and then the minimum of the answers like I described for the complete cases for the second part, and then you do a similar thing for the rest of the way in the third block, which is from here to here. In terms of solving this, so the middle part can be solved in fairly short amount of time because you have the answers ready. So you just have to look them up. So some constant time operation, array lookups and comparisons, and you're done. The only part which comes in is the smaller blocks, that the partial blocks. And to do that, you can basically do the naive solution if you wanted to. But you just generate the solutions of the smaller blocks, and you do in-block RMQ query as you would do in the dynamic programming solution or the naive solution. And you basically get the answer to that. So that's one part. So I guess an observation here, and this is where the +1, -1 will come in. You can observe that if you have two arrays in which every element differs by some constant amount, then the RMQ for one array is the same as the RMQ for the other. Basically, you're taking that constant amount and subtracting it from all the elements of that of the second array, and you basically have the same array twice. So, and this is very helpful in Euler tour because if you see the whole structure of an Euler tour, you'll see that there's a lot of repetition in there. So a lot of these blocks tend to be repeated. Or so instead of computing whatever, 2n by log n blocks, you might need to calculate lesser number of blocks because they all differ by +1, -1. And if they share the same structure, you don't need to recompute them. You say that this part looks exactly like this part, and hence I don't need to recompute this. So if you take either one of these arrays and you normalize them, you basically have an array which says +1, -1, +1, -1, which, if you think about it, you can represent it as a bit array, a bit vector, which wherein 0 can say it's a plus, it's an increase in value, and a 0 can say it's a decrease in value, and a 1 can say it's an increase in value, because you just care about how much is the difference. And given that the total number of such arrays can be 2 to the power log n by 2, because every bit can have 2 values, and the total length of the bit vector would be log n by 2 and all that. So 2 to the power log n by 2 minus 1 would be the total, the total length, the total number of such vectors, such normalized blocks, which is sort of, which if you apply some more math, and it basically comes down to O of under root of n. And if you're interested in the math, I would want to show it, but a little later, I guess. So you basically have O of under root of n normalized blocks that you need to possibly search to get an answer to your solution for the generalized RMQ problem. So this is how it kind of condenses. So you have the regular dynamic programming solution, which is O of n squared, O of 1. And this solution is applied on up to O of under root n normalized blocks. So we create O of under root n tables, each of size log of n, and then the queries still take, and when you compare it to the original thing, you get your representation is basically you plugged in the under root n over there, so you get under root n log square n, which also which is much less, still much less than O of n squared, and is now O of n. And what you get here is these vectors, which most of the time would be repeated because you would have repeating structures in your trees, but not necessarily, but still you would be O of n under root n individual normalized blocks, and you can look, you can do the regular old lookup, and you would get your answer. So where does this land us? So we have each in-block lookup, like from the previous slide, that gives you O of n pre-processing time to construct each of those, under root n blocks for lookups which do not completely match the boundaries of your blocks. And then you pre-process your A prime, which contained the minimum of these blocks. So you construct a sparse table over, you do the range minimum query sparse table algorithm on the A prime array that you calculated over here. So that again will give you O of n. You add all of these up. So O of n plus O of n plus O of n still gives you O of n. So your total preprocessing complexity turns out to be O of n again. Someone with significant digits is dying there. But query, but that's the magic of O of n and big O notation. Query time is, again, O of 1 lookup, because every single time you're basically doing either minimum of a bunch of things, or you're doing array lookups, which is all constant time. So it doesn't change the overall constant time lookup in all these cases. So you again get O of 1 as your query time complexity, and that's it. So you have an algorithm which is constructed over smaller instances of your array, and you get an answer by combining those answers. So we started with RMQ, and I'll cover a Cartesian tree in a second. But so now let's say you have an answer for the RMQ problem. You can construct the LCA. You can construct a tree out of it if you consider that. Where did I put? Oh, yeah. So you start with a LCA. You start with RMQ problem. So you're asked, give me the minimum, the range minimum of I and j. You convert that to LCA by doing a Cartesian tree, which basically says, given a array, I would divide the array into two parts at the minimum of the minimum value in that array. So if do I have a no? Okay. So if you have an array, just imagine you find the minimum in the array, and that forms the root of the tree. And the left child and the right child is basically all the elements to the left of the minimum and all the elements to the right of the minimum. And recursively, you build a tree out of the whole structure again. And what you end up with is you took a regular array and you constructed a tree out of it. So instead of answering the range minimum query answer, you have a tree. So now you can answer the least common ancestor problem on that by answering the ±1 range minimum query solution, by applying the ±1 range minimum query solution to the Euler tour of this Cartesian tree that we created. And and that has, and as it shows, you do the whole thing about dividing it into sub blocks of length log n by log n, and doing all that. And what you end up with is a final solution to range minimum query and LCA problem in O of n and O of 1. I know it kind of went into the weeds at the end, but maybe if I sort of showed this. Let's see. I have so this sort of helps answer this. So this is another presentation which sort of gives you an idea on what the last part is. Yeah. So this is what I was talking about, how you would construct, how you would take a range minimum query, convert it to a LCA problem, and then convert it to another range minimum query problem to get the answer to the LCA problem, which would give you the answer back to the original RMQ problem. So it's inception out here. So first thing to look at is the whole definition of Cartesian tree. So what you do in here, the labels on the nodes are the positions of the corresponding value. So you take the whole array. The minimum is 7, which is at position 4. So you construct that as the root node, and everything to the left will be on the left child of that root node, and everything to the right of that node of that position in the array is to the right. So so on the right you say, 10 is the minimum, so 0 is the node at the first level, and then so on. So once you have the Cartesian tree, you sort, and this is sort of the rule how to build them incrementally. So you take a root node and you always add it to the rightmost path, because you're growing an array, right? So if I was growing it like this, you would build it just one node, so it's a root node lying out there. The second node comes in, so it's always added to the right, because it has to be the right child of it. Then every time you add, you look at the current rightmost node in the tree, and then you compare. You basically say, I will climb up till I find the place where I can insert this node, at which point I would do this kind of thing. So basically, you start off with U, X, and then V wants to get joined to this tree. And the way you join it is by separating out U and X and inserting V in the middle, and X sort of becomes its left child, so that when you do the Euler tour traversal of this tree, you get back the array that you started off with. No, sorry, the DFS traversal of the tree you get back, yeah. So this sort of shows you, this shows you how the tree is formed, and this specific example shows you how it sort of rearranges when a smaller value comes in after a bigger value. So 10, then 25, and then when 22 came in, it climbed one level up because it was smaller than 25. So you want to divide that at 22. So it came up, separated the child of 10, which was 25, and added it as the left node. And at this point, the same thing continues. It again adds, and finally, so 10, it just gets added over there. And when 7 comes along, it keeps on rising till the point it's at the root node, at which point it just says, I'm the root node, so everything comes to the left of me. And you end up with a tree which looks like this. So this gave you a tree which can now be solved in the LCA problem. So you can take this, you can do the Euler tour on this, you can generate the levels and the representative nodes, and then you can solve that problem. Because now you know how to do the +1 - 1 RMQ, because that condition would be satisfied. And you would get some node in this tree, which would be the range minimum, which would be the lowest common ancestor of some two nodes. So let's say I was taking 1 and 5, and the minimum, the node which is the least common ancestor in this tree would turn out to be 4, which I'm going to say can be answered by the +1 -1 RMQ because we saw that. And we would get 4, and 4 would give you, 4 is the position of the lowest common ancestor, which is, and this tree was derived out of by doing the Cartesian, is a Cartesian tree over the original one, and the way it's generated would give you the minimum the minimum node, which is between the values at position 1 and 5. So it would give you the answer to something like the answer to the range minimum query of A of 1 through A of 5, which would turn out to be A of 4 from the LCA problem, and hence would be 7. So it kind of went back one level at a time. So, RMQ of A, ij is LCA of ij, LCA of C, which C is represented as the Cartesian tree of A. And the proof is that. So to see it more concretely, so over here it's showing you the example of finding the RMQ of 5 to 8. So RMQ of 5 to 8 is LCA of 5 to 8, which turns out to be 6, and that is, in the original answer, it would be the correct answer, which is A of 6. And yes, that's it. You took the original problem, converted it to a LCA, converted it into another RMQ, converted it into the solution, turned it back again, and got this. So, yes. If I have some extra notes on this, which would sort of clarify any of the proofs that I did not go into, but yeah, that should be it. If you lost me anywhere, I can go with a whiteboard and construct it, which is generally how I saw this paper going down. You have to sort of draw the tree and trace it through to actually get an idea of how it's built.
Having a little trouble believing you that constructing the Cartesian tree is big O of N, if you're looking for things to go through.
Okay. Yes. So, okay. So let's follow this. This is my major train of, this is the basic algorithm, right? So every time you have to add a node to your, every time you add a node to existing, whatever you have constructed so far in your, in your tree structures, the tree structure so far would give you, basically, yeah. So so I guess it starts off like this, right? So you start off with the root node. Adding another node is, of course, easy. the thing comes in when you have to sort of backtrack and add it at a level which is not exactly always the rightmost path of. It's always added at the rightmost path, but it may end up in a position which is not the rightmost path, as it happened in this case, right? You started off with with 10 and 25, and you sort of switched it around by comparing 22 and 25, and the only thing which you did over there is swap the I guess if I think about it in pointers, you swap the parent of this to point to this one, and this one's left child to point to the previous subtree that you had.
But you also had to compare against 10 there. What if it had been less than 10?
Yes, it could have been the case like in this case, wherein you would have, you would basically go around comparing it to everything and, adding it all the way at the top.
When I'm adding 7/4 here, I've got to compare.
Sorry, say again?
When I'm adding 4
Yeah.
/7, which will become the root node, I start off.
You start off comparing the 3 to 4, and then you compare. No, you would. So you know where the minimum of the current one lies, right? It's always at the root.
Mm-hmm.
So you can. This is the last part of the paper which I sort of.
They just kind of asserted it in the paper.
Yeah, they sort of do just assert it and you go by it, but from the way I have understood this is, as you consider. It's okay. So in this case, the assertion which they make is every time you have to add an element, you either add it to the rightmost path, or you remove one and add it at to the flippy floppy thing at that position once you get to it. But I do agree with you that they sort of.
I might have to do up to n comparisons to figure out where I'm going to do that flipping flopping.
Up to n.
Or maybe up to log of n, I guess. Depending on the tree.
I will sort of agree with you. They sort of glossed over the part wherein they say how many individual operations of comparison it involves. They sort of took every mutation on the tree as a single operation rather than.
So actually now looking at it again, they say each comparison either adds an element to the rightmost path.
Yes.
Or removes them. So maybe it's that as part of inserting a single node, I may do more than.
No more than how many ever comparisons, individual comparisons.
But overall, it's gonna average out to exactly 2n comparisons in total. I think is what there are enough nodes where I'm doing one comparison and then.
Oh, you're saying like it amortizes to the cost of.
It's not every node can be the minimum.
Right.
You don't have just as many maximums as you don't have minimums.
Yeah.
I don't know the answer. to that perfectly, mostly because even the paper
think
sort
I've-
of glosses over
I
that
think
fact.
I've worked out and managed to convince myself that it's true now.
This looks almost exactly the same as heap construction. But I'm sure there's... Hmm?
Yes,
It's
they're
also-
defined as heaps,
Okay.
in which the root
Yeah.
node is kept at the minimum.
I've also never really understood that. So
Uh,
it would make sense that they're related problems.
Okay. But yeah, so it sort of goes into the whole thing about I guess going from one problem to the other problem, back to the first problem, and first problem special case, and then answering them in the reverse order. So that's basically what it is. You do raise a good question as to exactly how many comparisons they do in the Cartesian tree and how they come up with O of n. I haven't looked very much into detail.
I
with
think
that.
I've managed to convince myself that it amortizes out to 2n.
I can see that, but I wouldn't.
I
I
could
can
prove
mentally
it to
see
you.
that, but I can't prove it. So
Given that someone else has claimed that they proved it, I'm willing to believe it.
yes. So yeah, so this was the last part of the paper, which was to convert it from all different things. And that's what we did, and except for the one hand wavy part, everything else was fairly concrete in the paper. That's it for RMQ. Hence is solved, and the world is a better place.
Very
Hopefully. And if you're interested, I recommend this implementation because it exactly follows the terminology and the structure as it is described in the paper. So you would actually find variable to variable similarity. So it is in C++, so that's one thing, but it implements each one of those algorithms, and it sort of goes through how to get it, and it actually works because I actually tried compiling it, and then for which you need a very specific setup. But yeah, you should, if you're interested, I will post this GitHub link. It's very readable code, and that was the whole point of the paper, to make a very implementable version of the original algorithm, which the 1984 or 19 something paper presented, and turn up with this. So yeah, and in your favorite language, I think there's a Python implementation for if someone is interested in actually reading what the code is, but yeah, actually not Python, I guess Ruby, but sure, it's as readable as it's going to get, I guess. So yeah, that's it, and end of story. Yeah, if anyone else is interested in presenting paper of your choice, or if you just have ideas about what should be covered, do let me know, or just on the meetup, you can just mention it, and I will try to either find people who would be willing to present, or I will ask you to present, or if you're interested, you can also present. Yeah, cool. Huzzah.